Good morning. Today we're talking about the atmosphere, we're talking about meteorology, about weather, a little bit of all of that. I like this picture here because you can see the Earth from space, and here's the night of Earth, and up here's the dark, cold space. But you see this little layer in the middle there? That is the atmosphere. That's what we're talking about, and that's a pretty important layer. And you can kind of see some structure there to it. Some of that's reflection of the Earth, etc. But there are some layers, and we'll be talking about that, what it's made of, what it's good for, and let's just see what happens here. The first thing you should know about the atmosphere is that it's about 78% nitrogen, followed up by 21% oxygen. You notice that that's about 99%. So almost everything is nitrogen or oxygen, with the vast majority being nitrogen. There's some other stuff in there: argon, carbon dioxide. There's trace amounts of other gases, helium and neon, etc. There's a little bit of water vapor, anywhere from 0 to 4%, depending on where you are. Arizona has 0. South Carolina has 4%. I'm just kidding. Particulate matter, soot, soil, salt, spores, all this stuff that gets stirred up into the air. You know, if a bulldozer goes by, then that's going to kick up a bunch of dust, and that goes in the atmosphere for a while until it falls back out. So there's some of that kind of stuff too. The layers of the atmosphere look like this. You can see the Earth down here. The closest layer is called the troposphere. The troposphere reaches up about 6 miles or 10 kilometers, and so that's a little bit over the top of Mount Everest. Passenger jets fly in the high troposphere, low stratosphere, somewhere in there. So that's the closest region that we have. The next one is called the stratosphere, and that's a pretty important layer. Most especially, there's something called the ozone layer. It's supposed to be shaded through here, so pretend like you can see that. And if you kind of hold your finger over the screen right there, that could be the layer, right? Ozone layer goes through here. We'll talk more about the ozone layer in a little bit, but the stratosphere is the second layer. The next one up is called the mesosphere. And then there's actually a fourth layer above that that's not shown in this picture. I don't really care if you know these distances or not. It's about 6 miles to the top of the troposphere, then about 30 miles to the top of the stratosphere, and it keeps going. I've got another picture that's got the fourth layer and has some more information. But let me tell you about this ozone layer real quick. When light comes in from the sun, there's all kinds of light, and there's all kinds of stuff coming in from space. Some of it's harmful. And of course, ultraviolet comes from the sun, and ultraviolet is harmful. That's what gives you skin burn or skin cancer or retina damage. It can hurt crops. It can do all sorts of bad stuff. So what's interesting is that there's this layer in here called ozone, which blocks a good bit of that. Ozone is nothing but 3 atoms of oxygen tied together in a covalent bond. Normally, oxygen forms O2. Right, 2 atoms of oxygen tied together in a molecule. This is 3. It's bigger. It's more massive. It has the ability to stop these ultraviolet rays coming in from the sun and from space, and that protects us here. So there's a couple things already that we can see from the atmosphere. One, we've got all that oxygen, and we need oxygen to breathe, so it keeps us alive that way. This ozone layer protects us from the from the ultraviolet, so that's the second way. There's a couple other ones I'll show you here, but that ozone's pretty good stuff, at least up in the stratosphere. Here's the other picture I was telling you about. You see the troposphere here and the stratosphere there, and the mesosphere here. The fourth layer is either called the ionosphere, if you're interested in the ions and how radiation coming in from outer space affects the gases up there, or it's also sometimes called the thermosphere if you're interested in temperature. So we'll just call it ionosphere, I guess, like you see here. There's one other region that they've identified. This is the tropopause. It's kind of a transition area, transitional region between the troposphere and the stratosphere. So this one's put that on there too. You don't really need to know that. If you knew the 4: troposphere, stratosphere, mesosphere, ionosphere, I'd be happy as a clam. All right. There's an interesting thing that happens here with the temperature. if you got in a hot air balloon and you started rising up through the atmosphere like this before you got to black space out here, it'd be about 60 degrees on the ground, and then as you rose, the temperature would fall, and something like negative 55 degrees up there at the top of the troposphere. As you go into the stratosphere, you actually warm back up. This has 60 degrees Fahrenheit. I suppose that number's about right. And again, I'm not interested in the temperatures, just an interesting thing that happens here. Why does it warm back up as you go through the stratosphere? Well, the stratosphere is real good at absorbing energy and holding that energy. So when the sunlight comes in, there's a region there where it catches it. The ozone layer here, this one did show up in the picture, so you can see the shading there. That absorbs some of that energy and that heat, and so it's warmer up there. And there are other gases that do that. As you go through the mesosphere and into the ionosphere, though, it gets mighty cold. So take along a jacket on your hot air balloon ride. You won't make it past about here anyway, but that's okay. Check this picture out here. Here's the ground, and as we rise up through the troposphere here, notice that at the top of the troposphere, about 90% of the gas molecules are below this. 90% of the atmosphere is within the troposphere. All right, so these other three layers, the stratosphere and the ionosphere and the mesosphere, those get really thin air. If you've done any mountain climbing, you know that the higher you go, the less gas there is, the less atmosphere, the less air, oxygen, whatever you want to measure. And it's tricky to breathe up on the top of a big mountain. Biggest mountain I've ever climbed is about 12,400 feet out in New Mexico, and you take a couple steps, and then you stop and you breathe a while, and then you take a couple more steps, and that's back when I was quite a bit younger and better shape. So the air gets really, really thin. Up here, 99% of the atmosphere is within the stratosphere, or there at this point and below, and so there's hardly any gas molecules up there, but it's still an important region of the atmosphere. I'd like to tell you a little bit about the ozone up in the stratosphere. Here you see 4 pictures. We'll look at this one, and then we'll step over here and like so. But ultraviolet comes in and hits regular oxygen. This would be a regular oxygen molecule here made up of 2 oxygen atoms, and that ultraviolet has enough energy to break those 2 apart, to break that double bond, that covalent bond that we talked about. Splits up into 2 free oxygen atoms. Oxygen doesn't like to be alone. It's going to go find another something to bond to. And so what it finds here is some more oxygen. If it finds an oxygen molecule here, then it works out a new type of covalent bond to make this ozone, like that, 3 oxygens in a covalent bond. Here's something about the ozone depletion, the ultraviolet coming in. The lines are meant to show, how much ultraviolet is absorbed within this ozone region, but don't get too excited about, well, there's 4 and 1 made it through. It's symbolic, okay? Up here is the ozone layer. You see the O3, that would be the ozone, and 3 out of 4 of these rays of ultraviolet light are blocked up there by the ozone. Again, I don't know that it's really 75%, but just a number to kind of work with. All right, 1 comes down here. This 1 gives us all the problems that we mentioned: skin burn, skin cancer, all that. All right. There are chemicals that we used to use a lot of called CFCs. And CFC stands for chlorofluorocarbon, and so you can see that it's a molecule that has chlorine, it has fluorine, and it has carbon things in it. These chemicals are really handy. You can make refrigerants out of them for your refrigerator or air conditioner. You can make propellants for spray paint or hairspray or whatever. We just had thousands of uses of these things, and they were really handy. And then somebody started noticing that we were getting holes in the ozone, and so that was not good. That was not good at all. What they noticed was they would go around and they would count how much ozone there was up here in the ozone layer, and that was being depleted by these chlorine that were part of the CFCs. Here again, it's a complicated process, but we use the CFCs on Earth. They move up through the atmosphere, especially in cold regions like the South Pole, and the ultraviolet breaks those molecules apart. The chlorine can then attack the ozone and pull one of the oxygens off, and so you're left with O2, which won't stop ultraviolet light. It looks more like this picture right here. I had a couple of ozones over here. I've only got one there. Again, that's just representative. But now I've got a whole lot more ultraviolet coming through, and all of those problems come about. There are a lot of things that these are some of the sources that hurt the ozone layer. Solvent cleaning products, sterilization, refrigeration, air conditioning. This was a big one here. Cars and houses used to use Freon, which was a coolant that they would put in the air conditioners. I can remember working in hardware stores, and you could just buy a little can of Freon and take it out and hook it up to your car and recharge it. And then all of a sudden they banned it, and it just disappeared overnight. All that stuff, people bought it up so they'd still have it. Now you can still go to the car part store or Walmart or somewhere and buy coolant, but it's a different coolant. They found something that doesn't have the CFC properties that would hurt the ozone, and so we kind of fixed that a little bit. Foam products, aerosols right here. Spray cans used to use a lot of CFCs. Now we use something else. I don't know what, and some other stuff, halons and whatnot. Okay, here's a kind of a picture of this ozone hole in the ozone layer that we talked about. You can see the dates here. This is 1980, and what they're doing is they're measuring how much ozone there is in the atmosphere. So this is the scale. Red would be a lot of ozone, and then as you move this way toward that deep purple, that is low counts of ozone. The Dobson units are what they measure that in, and you can see here's about 500 Dobson units down to 100 Dobson units. So somewhere on that scale, it's color-coded. This is the South Pole we're looking at, and when they talk about the hole in the ozone layer, the big one is over the South Pole. There are other ones other places, but that's the big guy. Here it is here in 1980, 82. You can see it's darker and bigger, and this circle just keeps getting darker and bigger up to 2001 here. This is kind of an old picture. I need to get some new things, but this was kind of when we started noticing and started fixing things, or trying to fix it, and so that's the issue there. Smog is another pollutant, another problem that pretty much we introduce with the atmosphere. You've seen Charlotte look like this, and Charlotte's not much of a city, so you know that all the cars that we run, all of the air conditioners, everything that emits pollution, that goes into the air. It's got to go somewhere, right? And so that you get that brown hazy look over the city. This is a little map that shows air quality in the United States here on the eastern seaboard. And so looking here at South Carolina, you notice how green would be good along the sea, along the coast. You've got good air. There's not a whole lot of people living there. You're continually getting refreshing and mixing off the ocean currents and off the breezes and everything. So pollutants are being carried away. Here though, there's a little brown spot. You see that the brown, I don't know if that's orange or down here is probably this one, but there happens to be a pretty good sized city right there, right? That's Columbia. And so you can see where Columbia is from the air quality map. Right here you get a big brown stain. That would be Greenville-Spartanburg area. And so it runs right there. Here's, of course, is Charlotte and all the growth that it has. You notice Raleigh, Durham, Winston-Salem, all that's over here. And so it's interesting how you can see where people live by the air quality map. Up here's New York and New Jersey. A lot of industrialization, a lot of cars and buses and all sorts of stuff going on. So that's another region that we would see a lot of air pollution. like to tell you here about another nice thing about the atmosphere. If we think about the sun shining its light and its heat and its energy down on the earth here, you can kind of, they've mapped out how much energy goes where and stuff. 100% comes, of the 100% that comes to the atmosphere, 19% is absorbed up in the atmosphere by water vapor, dust, and ozone. 4% is absorbed by clouds. Some of it's bounced back out into space, either off the top of the atmosphere, off the clouds, or off the surface of the earth. But about 46% makes it down to earth and is absorbed here. It warms the earth. It helps crops grow. It keeps us warm and everything. All right. Now, at the same time, Earth is a hot ball in the middle of cold space, so it's losing heat all of the time. And right here, you can see that about 9% comes out because of long wave radiation. 6% of that 15 that goes back out is reabsorbed in the atmosphere. Right here, the atmosphere loses about 40%, and the clouds about 20%. And I don't care about the numbers. Okay, what I want you to think about is I've got energy coming in and I've got energy going out. And if I have too much energy coming in, that makes it too hot here, right? Or if I had too much energy going out, more energy going out than I had coming in, then it would get very, very cold here. And so what I'd like you to know here is that the atmosphere, in addition to giving us oxygen to breathe and keeping us alive, in addition to protecting us from radiation and keeping us alive, it keeps us warm enough and keeps us alive. So that's another reason I'm a fan of the atmosphere here. These numbers, you don't need to know them, don't need to even really try to think about them, but you can see that the balance is important. If something happened here to the atmosphere that held more heat in, then it would get hotter. If something happened, whether we did it or nature did it, whatever, if the sun all of a sudden started putting out more energy, if, whatever, that would change temperature here on Earth and our climate and our way of life and everything. We might have a shorter growing season, which meant we couldn't grow as much food, which meant, or if it gets hotter, then, the ice caps melt and the oceans fill up and flood the coast and all that. Just lots of variables going on here. Some people get real excited about this and talk about global warming. So I'm going to show you some graphs here. We're going to talk about it. I don't have a fixed opinion on this. Again, there's so many variables and so many possibilities that I'm going to leave it up to you to figure out what you think is going to happen and what is happening and what we should do about it. But these numbers kind of illustrate the point that we need to think about what we are doing to our atmosphere. Here's the first graph I'd like to show you. Two things going on here in this picture. You can see that they've been measuring pretty accurately since 1750. Two numbers: the carbon dioxide concentration and the temperature. The red line is the carbon dioxide concentration. The blue line is the temperature. And this graph cuts off about right here, 2005 or something. Okay, so everything after this point is sheer conjecture. All right, this part of the curve going crazy here, don't know that that's going to happen. That's what somebody drew on the thing. This we do know, and you can see here that the carbon dioxide has stayed pretty constant up through the 1800s. About 1850 it takes a little bump right there and it starts to climb. And we know, of course, that that's about the advent of the Industrial Revolution. And so the thought here is that as we burned a lot more coal and a lot more wood and a lot more gas and a lot more diesel and all that stuff, those fossil fuels release carbon dioxide into the atmosphere. And that is thought to explain this rise here in the carbon dioxide concentration. Okay? The blue line shows the temperature, and you can see that stayed very, very straight. You got to look over here on this side to see the temperature scale. So what they've done is they've set 0 here at where this traditionally lay. All right, so 0 runs right through here. If it goes up a degree, it's here. If it's 2 degrees here, 3 degrees, whatever. If it goes down, it's over here. Now, I should say that these are temperatures in Celsius. So that works out to about 2 of our degrees, 2 degrees Fahrenheit roughly 9/5. So keep in mind that we really have to double everything here. Some interesting things happened. You can see the temperature kind of got a little crazy right in here, but you can see a gradual rise there, right? If you think about here's where it used to be, then you can see that it's come up here. We're talking about a degree maybe or two. Again, everything after this point is conjecture, what might happen. So here again, if this blue line is correct, if somebody said, well, I think it goes over here and it goes up 2 degrees Fahrenheit, that's about 4 degrees Fahrenheit, and we can see some effects of that already. We see the glaciers on the mountains melting. That puts more water into the rivers, into the ocean. We can see the ice caps melting. We can see droughts that we didn't have before. We can, there's lots of factors, lots of variables. Everything influences everything else. So this is tricky business figuring it out. But when you hear about global warming, that's what people are concerned about. What if we're releasing enough pollutants to trap more heat than we used to? Carbon dioxide here is graphed because it's known to be a greenhouse gas. It is when you go to a greenhouse, they make greenhouses to grow plants in because the glass holds the heat in. The sunlight comes in, and then it's changed to a short wave, and it warms that infrared, and it warms that up, and so that traps heat. In the same way, carbon dioxide traps heat in an atmosphere, and so as our carbon dioxide level goes up, our temperature should go up. We look at planets like Mercury, Venus, which has a lot of carbon dioxide in the atmosphere, and it's 800 degrees, and I don't think we want our planet to do that. So now they've got very high carbon dioxide, and we're not anywhere near that. But I think you can see that the balance of what we do can change things, and sometimes small changes have huge effects. And so that's the concern here. Again, a lot of debate, both sides of this. Some people believe in this very strongly. Some people say it's all bunk. It's still kind of open in my book, and we'll see what happens. I got one more graph here. Same kind of thing with the temperature curve here. These guys have made 3 projections. Best case, they see it doing that purple line. Worst case is the blue line. Reality says it's probably somewhere in the middle. And if we were tracking along here at, say, 15 degrees Celsius, the green line takes us up to 17 degrees Celsius. Again, that's about 4 degrees Fahrenheit. So, but those projections could be way off, either not high enough or too high. So it'll be interesting to see what happens and what we can do about it. My thought on it, I don't know whether this is a real problem, whether it's a human-caused problem or not. I do know that this is the only planet that we are ever going to get that has everything that we need for life. And it is in our best interest to do what we can to take care of it. Enough said? All right. Here is the water cycle. You saw this back in elementary school or something, but let me show you real quick here. When it rains, we call that precipitation. The water falls to the earth, makes little creeks. Creeks make rivers. Rivers run into the ocean like this. All along the way, you get evaporation. The sunlight comes down, and it gives that water enough energy to change from liquid water to water vapor, a gas. And then it rises into the atmosphere, forms clouds. Those clouds come over. When the weather conditions are right, you get precipitation. So there's a cycle there like that. All right. Some of this water doesn't make it to the ocean. It infiltrates. It runs down into the ground. And so you have these sources of groundwater. There's a lot of water up under the earth. And if you live out in the county like I do, you know that because that's the water that you live off of. You drill a well in your yard, and the pipe goes down. You got a pump down there that pumps that water up, and you drink that, and you bathe in it, and cook with it, and everything else. So that's an important source of water. We talked about relative humidity in lab. Again, it expresses the amount of moisture in air compared to the maximum possible amount of the moisture in the air. If you imagine a little box, if you took a box or a peanut butter jar or something and closed up some air in your jar, then there's only so much water that I could put in the in between the gas molecules there. At some point it's going to start falling out, right? So in this example here, if a sample of air could hold 100 units of water, in my peanut butter jar, if I could get 100 units of water, but there's only 63 in there, then that would be 63 out of 100, or 63%. This relative humidity says here's how much water you have in the air compared to how much you could have in the air. It's an important number. If the humidity is high, then it feels a lot hotter. Our bodies sweat to cool off. The sweat evaporates and carries heat with it. If it can't evaporate because the air is saturated with water, if there's no more room for water, then that sweat stays on me and the heat stays with me, and I can't cool off. So relative humidity is a big thing here in South Carolina. You've got a pretty good feel for that. And if not, then just go out on a summer day and you'll understand everything you need to know. Lots of clouds. I like clouds a lot. I think clouds are pretty neat. And here you see the three main types. If you knew these three types, I'd be happy. Right here, the big puffy clouds are called cumulus clouds. Those are the ones that are pretty and we like to look at. These stratus clouds are kind of in layers. Can you see the layer structure there? Kind of running in lines back and forth. So when it's built up like that, we refer to those as stratus clouds. Cirrus clouds are thin, wispy clouds way up high in the sky. They form in the upper atmosphere, and since there's not a lot of air up there, there's certainly not a lot of water either, and so you don't get the big, full, puffy clouds. You get these thin, wispy things. All right. You should know, though, that those are the three big types, and you can combine them. There's all sorts of other clouds that go on here. Here's a cumulonimbus. See the big puffy cloud? But the nimbus there means that it's fixing to rain. Nimbus refers to rain. So here's a big puffy rain cloud. Nimbostratus would be layers of rain clouds. You don't really get rain from cirrus clouds because it's too high up, but you could certainly have that water vapor. If the air cools, then that's going to raise the relative humidity, because now cold air doesn't hold as much water vapor as hot water. So that water could certainly go somewhere. But if it's up there and it's cold, it may come down as snow, it may come down as hail, it may come down in some other form. All right. You get little castellations sometimes on the top of clouds, so that's got a name. Alto means high. Cumulus, it's a puffy cloud, but it's high. And castellatus means it's got the little things on top. So that's a weird kind. Here's some lenticular clouds, little lens clouds, and those are pretty neat to look at. If you want to see some, just do a search for lenticular clouds. And some of them look like UFOs and weird stuff. Those are pretty neat. But there are lots of kinds. The weathermen have little maps and charts that they use, and these are kind of the symbols that they use. I don't care if you know the symbols, but look at all the different kinds. Here's the cirrus cloud, and here's what they do for cirrostratus. If it's up in the stratosphere and it's a cirrus cloud, boom, you got that. So all the combination here is a cirrocumulus. If it's kind of in between cirrus and cumulus, you do that. So you could spend your life trying to learn all these things. Basically, the round lines are the big puffy clouds, so those represent cumulus. The lines are or these little hook things are cirrus, and the straight lines are stratus. So you can see how they've combined those to make it all work out. Lots of times when you have clouds, you can get lightning, and the animation over here on the side shows how that works. It's supposed to. Doesn't seem to be working today, though. Here are a couple of clouds. You see that you get a charge separation there. All of the electrons will they see Earth as a big grounding unit, place for charge to go, so they'll be attracted to the bottom. That leaves the top net positive. And when you get enough electrons built here, then they have the voltage to jump this region here and to form a bolt of lightning. Some of these lightning strikes are very impressive if you can, whether you're looking at them or if you can capture them with a camera like you see here. But you want to watch out for that stuff. The weather here is fine, thank you. You've seen maps like this: hot and dry and cool and wet. These are kind of the two factors that determine what's going on with the weather. Right here, dry and wet tell how much moisture is in the air, and hot, cool tells what the temperature is. And you might have a hot region here and a cool region there. When those meet, when that cool air up here mixes with the hot air here, then the air that gets mixed is going to all of a sudden drop in temperature. That's going to raise the relative humidity, and very often you'll get rain or some type of precipitation right there. So watch for that. On the weather map, they'll talk about cold fronts and warm fronts, and when those meet, you're going to have rain or something. Of course, the more water you have in the atmosphere, the more precipitation you get, and all of that. But heat is what really drives the weather. Right here you see an old radiator. The radiator gets hot, that heats the air rises like so, and cool air rushes in from the bottom to replace that air that rose away from the radiator. So you get this convection pattern here. And you get the same thing in cities, right? In cities you're running an awful lot of light bulbs and air conditioners and heaters and cars and tons of stuff that put off heat. And so you get an excess of heat here. That hot air rises, and cooler air will rush in like this to cool it up, not to cool it off, but to replace that air. And so you get a convection cycle off of that. At the ocean, you get a convection cycle. In the daytime, the land gets hot, and that heats the air above it. That air rises, and the air comes in off the cool ocean to replace that. So you get a cycle here. Nighttime, it actually goes the other way. The land cools off, but the water's been trapping this heat all day, so it's relatively warm. That air rises, and cooler air rushes in off the land, and it would go the other way. All right. Couple things here about climate. Of course, that some places in the United States get a lot of water, a lot of rain, a lot of snow, a lot of precipitation, and other places get very, very little. And so this is a little map kind of by region where you can see that Florida gets a lot of rain. That's here in the 45 to 63 inches of rain or precipitation a year. Right here in South Louisiana, South Florida, Western Tennessee, they're up in the next one, 63 to 81 inches. That's a lot of water coming down. We're in that 45 to 63, so that's good water. All the southeast here kind of has plenty of rain. You move up into the northeast, they're down in the next bracket, 36 to 45. And of course, these are kind of generalized. This is from 1998 over 1 year, but and so it's going to change year by year. But there's certainly a pattern. Right here's West Texas, and they only get 4.5 to 9 inches of rain a year. It's very dry. It's desert. It's I don't know why people mess with it. This is kind of an interesting region here, Washington and Oregon, Northern California. A lot of rain right there, and but then there's a line, and all of a sudden you're much less, right? You're down here in the arid region. So what happened? Well, there's a mountain range that runs right there. As moisture and air comes in off the coast like this, then it is cooled as it rises over the mountain. When it cools, it drops that rain. The rain never makes it over here to the other side of the mountain, and so that's what's going on there. Your book talks about 4 climate types. These are on page 258. If you could read through those and kind of match up what you see here. Actually, I think your book talks about 5, but you'll recognize these, of course. One of them is polar, up at the North Pole, South Pole, anywhere where it's really frozen. There are no trees. It never gets above a certain temperature, and that temperature's in the book, so look it up. We kind of live in a temperate region here, and they describe that. There's desert regions, and then there are tropical regions like South Florida, like Hawaii, like Mexico or something, and so those are different climate types. And if you look at a map in the climate types, you can see them here. Southeast, warm, mild climates. Right here's the west. That's a dry climate, right? Lots of desert in Arizona, New Mexico, and through there. The green is hot, wet climate, so that would be like your jungles of Brazil here, or in Central Africa, or Southeast Asia. The white would be your polar regions, very cold climates. So you can kind of see how that would work out just fine. The weather and the seasons are determined by the tilt of the earth here. And so let me real quick say, going on too long here, but here's the sun, and we make this path around the sun. As we do that, we're tilted either toward the sun here or away from the sun there. See how this stick, this axis of the earth is tilted away from the sun for the northern hemisphere there? So when we're tilted away from the sun, that's our winter. We don't get as much sunlight. The days are shorter. The sunlight is not as direct. It's spread out over a larger region, and it's kind of like facing away from a fireplace or something. Right here in the summertime, though, see the axis of the northern hemisphere, the top half of the earth here is tilted toward the sun. We're getting more direct sunlight. We have longer days. More energy means it's going to be hotter. And so it's that tilt to the axis that determines whether we're in summer. Here in spring, the tilt is kind of perpendicular to the direction of the sunlight. So it doesn't really affect it quite as much. Here, the top half and the bottom half, they're kind of getting the same amount. So that's a transition between this maximum solar energy and minimum solar energy here. So if I ask you to label these, if you could find the hemisphere that's leaning toward the earth, that's going to be the summer for that hemisphere. Meanwhile, the bottom of the earth is tilted away, so that would be the winter. Here it's going to be the next season, autumn for us, spring for the south. Right here, we're tilted away, so that would be winter. Meanwhile, the southern hemisphere is tilted toward the sun, so that would be their summer. And then fall, of course, our spring, their fall would be here again. We're kind of not leaning toward the sun or away from it, but like so. The seasons affect the weather, of course. Hurricanes come around in the summertime and early fall. Here's a map of the 2004 hurricanes. I'm just fascinated by hurricanes and trying to figure out where they're going to go and stuff. You can see that they wander all over the place. They have these crazy paths. Sometimes, like right here, for example, this was a bad year for South Florida. Jean came along and hit it that way, and Bonnie came through, and Francis, and there was about a little town there that got whacked 3 times that year. But here you can see the scale of what they're doing. Hurricanes start up here with the red and the darker reds. That's H1 through 5. That would be hurricane category 1, category 2, category 3, 4, and 5 hurricanes. If it's not as strong as a hurricane, it's called a tropical storm, and you can see that's marked in yellow. So right here, Lisa was a tropical storm, and then all of a sudden it got enough energy to be a hurricane for just a little bit, and then it went back to tropical storm. Alex over here was a tropical storm here, but then it picked up strength, was a hurricane, went to a strong hurricane, but it was out in the middle of the ocean. And I don't know if that's 4 or 5 there, but then it went back to a category 2 maybe, and then back to a tropical storm. Notice that all these hurricanes originate in the same region down here. They're all coming off the coast of Africa. There's a lot of reasons for that, a lot of factors that determine where a hurricane is, how strong it is, and if it even is. But the water temperature, the air temperature, the amount of water in the air, and the dust off of Africa, all of those play into when we get hurricanes. All right. Tornadoes are the problem for the rest of the country, right? This is kind of prime hurricane target here. The Midwest gets more tornadoes, and so everybody's got to worry about something. You can see here, of course, Florida gets both. So, but a tornado might look something like this. I've never seen one. I've always wanted to catch one, Not too close, you understand, but I think they're pretty neat. The scale here is color-coded by how many they have had. It says between 1958 and 1996. So over this 40-year period, if a county got 56 to 118, they shaded it dark red. White is only 1 to 8. So Utah is pretty safe here, and Arizona maybe, but these guys are getting slammed. Here in South Carolina, you can see some red spots. So 18 to 30 there in 40 years. Of course, we know that we've had a lot recently here. All right, that's what I've got. Thank you much.